As a new team, designing the car entirely from scratch, with no previous results or data to go on, much of our design philosophy has been built upon simplicity and low cost. The design process has been a steep learning curve for all involved, and research and redesigns have been the most considerable time investments. We split our organisational structure into 4 separate design teams, plus a business and costing team. The 4 design teams comprise of suspension, steering and braking, powertrain, chassis and ancillaries. It has been my responsibility to oversee the overall design of each team area, which includes control over each design process, project management and ensuring everyone is working towards the same common goal.
As the team has essentially started from new, the main focus of the suspension geometry was to ensure that the car would inherently handle in a predictable manner. So we focused on reducing detrimental camber or toe changes whilst the car is under load, such as bump steer, and how the car behaves under cornering using the SUSPROC software. We soon found that many compromises had to be made with the packaging of the car, as the chassis itself had to go through many iterations and the suspension had to be altered to fit around this. Reducing roll centre migration was a minor consideration, but we didn't focus on it completely, as there's many other factors which can affect it that are not inherent to the suspension geometry. For next year we'll be taking this design forward and fine-tuning it, such as trying to introduce anti-dive and anti-squat, and we'd also like to look into narrowing the rear track to see how this affects the handling and the overall packaging of the car.
We opted for a tubeless face frame chassis to minimise cost and allow for simpler manufacturing and alterations. Low weight and centre gravity with high torsional rigidity were the design goals, and were initially constrained by the suspension geometry and FSAE rules, but the need to make alterations due to packaging requirements became apparent. FEA testing indicates potential 2,500 Nm per degree of torsional rigidity, and once manufacturing has been completed, this will be tested with applied loads and strain gauges.
This year has been a good year for our powertrain team. The Yamaha R6 that was left to us by the previous team is now up and running and has been subjected to a series of dynamometer tests. Results from this testing have been very positive, showing us that the engine is sound. With this testing complete, we've moved on to design and manufacture of a new testing rig, which enables us to test new components on the engine on the dynamometers that are available at our university. We've also made significant design progress this year. As our engine as standard runs on carburetors, a significant amount of work has been done on converting it to fuel injection. Our inlet design is based upon proven engineering principles such as Helmholtz resonance and pressure wave tuning theory wherever possible, or has been designed and optimized with computational fluid dynamics, and certain parts have been prototyped to verify these results.
Being one of the 3 first years in the team, I feel I got to grasp with the software fairly easy, having previous experience in other CAD systems. The CAD software we use is fairly simple, yet still complex enough to allow us to get the complexity of the designs and parts we need in order to extract the maximum from the car. We have also used a wide variety of simulation software and testing software to ensure all the components will function correctly and how we want them to. To test the uprights, for example, we use FEA testing, allowing us to find out the maximum stresses in the design could take whether it would work on our car. We also carried out this on the chassis to work out deflection levels and maximum stresses. To ensure the airbox performed correctly, we use CFD testing, looking into flow analysis.
My responsibility within the team is the design of the ancillary components. This involves the design of components such as the pedal box, impact attenuator, and safety equipment including fire extinguishers. When designing components, we went through many iterations, the focus being on finding the balance between functionality, weight and strength. The components have been designed using a CAD package and then FEA simulated to ensure the components perform as required. We have made use of rapid prototyping in order to visualize and test fit components before final manufacture. Through the design phase, it has been important to consider the manufacturing methods and design the components accordingly.
As manufacturing leader, my role within the team during the early parts of the year was to be part of the design process and oversee the CAD modelling, so it meant manufacturing capabilities available to us at the university. Once manufacturing began, it was my responsibility to coordinate with faculty technicians and team leaders. Once parts were finalised, myself and several other team members began marking up jigs, cutting material and manually machining material. Several parts were also machined using a CNC milling machine and printing using a high-density rapid prototyper. Components that were manually machined range from the wheel spindle to wishbone rod end sleeves, with the hub and brake disc carriers being CNC milled. The uprights and pedals were high-density roughly prototyped to reduce machining workload.
My responsibilities in the team have been to deal with the business, costing and sponsorship. This has been a very involved process as we're a new team and we've had to start from scratch. We've created a sponsor pack that we send to businesses to try and aid our funding, and I've also been involved in working on the costing and business presentations. This year we've aimed to design a car with low cost and high sustainability that we would aim to improve on in years to come.